You know what? I forgot to open the folder for today. Let me do that real quick before we start because we're going to need it later. Okay. So today's topic is 11.9 double replacement reactions. This is the last type of chemical reaction that we're going to be discussing. Tomorrow we're going to start something new. But today, let's finish up types of reactions. All right, bartering, which is basically a fancy word for trading for services or other products. Bartering has been part of society for a very long time. Okay, people you have been bartering for years, for centuries, right? If you're a farmer, you make milk, well, you can trade the milk that you get from your cow and trade it for something else. You can trade it for services. Maybe you need some new horseshoes for your horse. I don't know. Maybe you want some money, okay, so that you can buy some clothes for your kids. I don't know. Now I know my husband on YouTube, he says that there's this guy who like barters like nobody's business. And he starts off with something very small. And then by the time he ends up with a new car, it's happened. It's happened. Okay. I don't know his name. Maybe I can get it from my husband. I just know that he told me about it. He didn't really tell me who he was. He just told me that this guy is an expert barterer, and I kind of checked it out, but I really didn't pay attention. But today we are going to talk about trade, because in double replacement reactions, it's about trading elements within a compound. All right. Who's going to help me? Don't volunteer all at once, guys. Anybody? I don't hear anybody. Caitlin, it's a short paragraph. Can you help me? Caitlin?
The practice of barter trading one thing for another has been in existence for a very long time, and the illustration above items like chickens were bartered newspaper. We have something unborn and another new one. So we trade and we eat, have something new. So some chemical reactions are like compounds, swap parts, and you have a new one for you.
All right. Okay. So in this picture, you got doesn't look like he's a very, rich man, right? You can tell that, his clothes aren't as nice as the guy from the newspaper company. But either way, he's offering the newspaper guy chickens, right? Everybody loves chickens. And he's saying, okay, if I give you some chickens, you give me some newspapers so that I can sell and make some extra money for my family, because maybe I need a doctor, maybe I need to buy clothes for my kids, maybe I need to buy new shoes for my kids. You never know a person's situation. But either way, we know what's happening, right? We know that he is trading something that he has, a lot of, for something that he needs. Okay. And in a double replacement reaction, the same thing happens, right? In this case, compounds will switch elements within the compound uh, to make a new compound. All right. So today's topic, double replacement reactions. A double replacement reaction is a reaction in which the positive and negative ions of two ionic compounds exchange places to form new compounds. Okay. So first off, you're going to be working with ionic compounds, right? When you have ionic compounds, you're dealing with cations and anions, right? And in this general reaction of a double replacement reaction, also known as a double displacement reaction, you have element A. Element A and element C are positively charged cations, right? the T in cations means that it's a positive, right? Looks like a plus sign. And then elements B and D, right? B as in boy, D as in dog, are negatively charged anions. And either the anion switch or the cation switch. But you can never switch a cation with an anion. They have to both be cations or both be anions. You cannot have a positive exchange with a negative. That's impossible. Double replacement reactions generally occur between substances that are in an aqueous solution. So they're usually dissolved in water. In order for a reaction to occur, one of the products is usually a solid precipitate, a gas, or a molecular compound such as water. Okay, sometimes, not all the time. Okay, but just keep that in mind. So before I get started, before I show you your first Pear Deck question, I want to tell you something. When it comes to double replacement reactions, the thing that makes them unique is that you're going to have two compounds. You'll have a compound like A and B, you'll have another compound C and D, and then they're going to be doing some switching, right? But you'll still have a compound and you'll still have a compound. In a single replacement reaction, you'll start with an element, you'll end with an element, and then you'll have compounds. In a combustion reaction, you can figure it out because combustion reactions always have oxygen and then carbon dioxide and water. Okay, so those are easy to spot, those are easy to eliminate when you're looking for double replacement. Another thing that you have to remember is that when it comes to synthesis, when it comes to decomposition, you're going to have two reactants and one product for synthesis. In a decomposition, you'll have one reactant making two products. So you can easily distinguish those from a double replacement. So when you are tackling this question, because it says circle the equation that represents a double replacement reaction, you can easily eliminate some of these reactions. So right now, I want you guys to circle the one that is a double replacement reaction. Where do I have 4 compounds? 4 compounds. Okay, and remember, compounds, you always see 2 capital letters or more, 2 capital letters or more, 2 capital letters or more, 4 times. 2 on the left side of the arrow and 2 on the right side of the arrow. So if you have one product or one reactant, scratch it out because it's not possible for it to be considered double replacement. You always have 2 reactants and 2 products, okay? 2 reactants and 2 products. 2 and 2. Okay? Which one can we eliminate? Which one only has one reactant or one product that we can say, you're out? Which one? Reaction 1, reaction 2, reaction 3, or reaction 4? Which one can we say, bye-bye, you're out? Okay. Jeremiah says that we're going to get rid of reaction 2. Yeah, it is, but it's not because we only have one product or one reactant. It's the fact that we know that chlorine is an element, iodine is an element. That's not a compound, right? Chlorine and iodine are what we call diatomic molecules. Okay, but in order for it to be, and remember, molecules are covalent. So the fact that I have chlorine as a reactant tells me that that's out. What else is out? What else gets eliminated? What else has one reactant or one product? Remember, I'm looking for 4 compounds. Oscar, which one has 4 compounds? Caitlin, which one has 4 compounds? All right, Jeremiah says number 3. Let's check it out. Okay, this is an element, sodium, iodine. So this is a compound. Very good. Lead, nitrate, That's another compound. Okay, I'm starting off good. There are 2 compounds on the left. Let's look at the right. Sodium is an element, nitrate is a poly, but it's a compound. Very good. Lead, iodine, a compound. So is this a double replacement reaction? Did iodine switch with nitrate and attach to sodium? Yeah, check it out. Nitrate was with lead. All of a sudden, on the product side, he's with sodium. And look, who is now attached to lead, right? Everybody see that? Iodine used to be with sodium, now he's with lead. Sodium used to be with iodine, now he's with nitrate. They did a switch, they did a trade. That's definitely a trade-off, right? Yes. This one, the first one, we can eliminate because I only have one product. It's eliminated because I only have one product. There's no second product. So number 1 is out. Number 4, check it out. One reactant out, right? It's out because double replacement reactions always have 2 reactants, 2 compounds. So this guy is out. Great job, Jeremiah. I'm glad somebody's listening. I don't know. I already called on Oscar. I called on Caitlin, and nobody's answering. All right, now let's talk about forming precipitates. And precipitate is just a fancy word for saying 2 liquids are making a solid. A precipitate forms in a double replacement reaction when the cations from one reactant combine with the anions from another reactant to form an insoluble ionic compound. When aqueous solutions of potassium iodide and lead 2 nitrate are mixed, the following reaction occurs. All right, let's check it out. We have potassium, we have iodine, and iodine, let's look on the other side, is now attached to lead, right? Lead iodine basically kicked out nitrate and said, hey, that's my spot. Nitrate ends up with potassium, and you can see it here, and we have brand new compounds. And lead iodide just so happens to be our precipitate. Everybody see that there? There are very strong attractive forces that occur between lead and iodide, and the result is a brilliant yellow precipitate. The other product of the reaction, potassium nitrate, remains soluble in the liquid. So it's still dissolved, right? Those ions are still there. But you can see in yellow, look at that beautiful lead iodide. Lead 2 iodide. Beautiful red, yellow color. And that happens almost immediately. As soon as you drop it, boom, you see that yellow solid starting to form, or that yellow precipitate. All right. Another possible product is the formation of a gas. All right. So anytime you have double replacement reactions and you produce bubbles, right? If you see something, you mix 2 liquids and all of a sudden you see bubbles being released, that's gas that's being escaping, right? For example, when solutions of sodium sulfide and hydrochloric acid are mixed, the products of the reaction are an aqueous sodium chloride and then a hydrogen sulfide gas. Okay? And you can see here, sodium. He used to be attached to sulfur, right? Sodium and sulfur. Let's check it out on the other side. All of a sudden, sodium is now attached to chlorine. So what happened? Chlorine used to be with hydrogen. He's like, nah, I'm gonna go and I'm gonna say, hey, sulfur, that's my spot. Sulfur gets kicked out and says, ooh, I'm gonna bond with hydrogen. There it is. Sodium chloride, hydrogen sulfide, and check it out. This is our gas. Hydrogen sulfide is what's gonna escape from the solution. All right, now let's talk about forming molecular compounds. Another kind of double replacement reaction is when you produce a molecular compound as one of your products. There are many examples in this category of reactions, and many of them produce water. Many examples in this category are reactions that produce water. Okay, so anytime you are forming this molecular compound, you're actually forming water. And this is also known as the subcategory of acid and base reactions. When aqueous hydrochloric acid, and you can see the word acid in there, is a big hint that you're dealing with an acid. It reacts with aqueous sodium hydroxide. Hydroxide. The fact that it says hydroxide turns on the light and says, ooh, I got a base. I got a base. And if I have an acid and if I have a base, I know for sure my product is going to be a type of salt and water. Okay? And you can see that here. Hydrogen with chlorine. Sodium with that hydroxide, right? This is the base. This is the acid. Chlorine is saying, ooh, I'm going to go and I'm going to kick out hydroxide because I want to be with sodium. Hydroxide's, no, I lost my place. Where am I going to go? I'm going to go and bond with hydrogen. And if I have H plus OH, that's going to be water. And you'll find it in the liquid form. And then you'll have salt. And it's aqueous because it's dissolved in water. Okay? Sample problem time. All right? And you guys are going to help me. Let's go to Jamboard. All right, write a complete and balanced chemical equation for the following double replacement reactions. One product is indicated as a guide. All right, so here's our hint. This is our guide. They're telling you if you have sodium cyanide plus hydrogen bromide, one of your products is going to be hydrogen cyanide. So cyanide is here, right? Cyanide is going to be like, oh, I'm going to go and bond with hydrogen. Bromine is like, uh-oh, I lost my spot. Oh, but there's one with sodium. Let me go and make a compound. All right, so let's write this formula for hydrogen cyanide. We need the symbol and we need the charge before I do anything. All right, I can't just write the letters together. I need to prove using my symbol and my charge the correct formula. Okay, so I'm looking for hydrogen and cyanide. Here's my valence sheet. Hydrogen at the very top. You see it? Hydrogen is H plus 1. Okay, cyanide. Oops. Cyanide, here he is. Capital C, capital N, negative 1. All right. If I have H with a plus 1 charge, cyanide with a negative 1 charge, what's going to be my formula? And then my second compound is going to be between sodium and bromine. So again, I'm going to go to the valence sheet. Sodium, sodium, sodium. Where are you? Oh, here he is. Sodium, Na plus 1. Uh-oh, where's bromine? Here it is, negative 1. All right. Negative 1. Oops, my bad. Supposed to put the other one first. Sodium, Na plus 1. Bromine, negative 1. What's going to be my formula for these guys? What's going to be my formula for these compounds? All right, so I'm going to rewrite the reaction. Sodium cyanide, aqueous, plus hydrogen bromide, aqueous. And that's going to produce hydrogen cyanide. What's my formula? What's going to happen, Oscar? If I have a plus 1 minus 1, what's going to happen? What's my formula going to look like? Right here. If I have a plus 1 and a minus 1, what happens here for this compound? Oscar. Oscar. Jeremiah. Caitlin. Yalexia. Mario. What's my formula here? What happens if the numbers are... What's going to happen if the numbers are the same? They both cancel out. Very good. Okay. So this guy and this guy is gone. And then everything else comes together, right? This guy and this guy is also gone because it's the same number. So my formula for the first one, HCN. And that is a gas. My second compound, NaBr, aqueous. We're going to assume it's aqueous unless they tell us it's not. All right? Okay, we have to balance. Okay, I have Na. Oops. I have Na. I have Cn. I have H. I have Br. What's my numbers? How many sodiums? How many cyanides? How many bromines? How many hydrogens? 1 sodium. Okay. How many cyanides? How many cyanides? How many? 1. How many hydrogens? 1. How many bromines? 1. Okay, go to the other side. How many sodiums? How many cyanides? How many hydrogens? How many bromines? Would you guys say that it's 1, 1, 1, and 1? Isn't it balanced already? Is it balanced, guys? Is it balanced? Yes or no? Is it?
Yes.
It's definitely balanced, right? A big hint is the fact that there's no subscripts. There's no subscripts. That means everybody is 1. It's balanced. All right, next one. Now we have ammonium sulfate reacting with barium nitrate, and they give you a hint that a precipitate of barium sulfate forms. So we need to write the formula for barium sulfate. All right. Barium. Where's barium? Here's barium. Ba plus 2. Ba plus 2. Write that down. Sulfate. SO4. -2. Okay. So let's write the formula, right? Or let's write the ions. So I got Ba plus 2. Sulfate -2. Okay. Let's see what's my other product. If sulfate bonded with barium, then that means nitrate is now with ammonia, right? Now sulfate bonded to barium, so nitrate is going to bond to ammonia. Okay, so if I need to go to the valence sheet and I need to look for ammonia right here. There's ammonia. Nitrate, NO3 with a -1 charge. NH4 with a +1. NO3 with a -1. What's going to happen to my formulas? Oscar, give me the formula for the first one in the chat. Diamond, give me the formula for the second one in the chat while I write the reaction. Okay? Please give me those while I'm doing this. So NH4, 2, SO4. I'm going to put that it's aqueous on top. Plus Ba, oops, NO3, and that's also aqueous. Okay, and what's my formula, Oscar? What's my formula, Mr. Oscar? If I have barium sulfate, what's my formula, Oscar? Oscar, 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 Mendoza. Don't make me look up your middle name. What's your Oscar? Oscar, Oscar. What's my formula, Oscar? What's my formula, Miss Diamond? What's good? Okay. Remember, if they're the same, they're going to cancel out. And what do? I just put them together. No plus in between. No plus in between. Oscar? What about here? BaSO4. Thanks, Alexia. BaSO4. Why? Because this cancels with this. For Miss Diamond, 1 and cancels with 1. And they're telling you it's a precipitate for barium sulfate, so I'm going to put an S. Okay, ammonium nitrate. And more than likely, that's going to be aqueous. Okay, I need a balance. Okay, NH4, SO4, barium, nitrate. Okay, how many on the left? How many ammoniums? 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 I'm gonna keep repeating until I get a response from y'all. I'm not gonna do this work by myself. Okay, how many sulfates? How many sulfates? How many sulfates? No, remember the 4's already here. So anytime you have a poly, Mr. Jeremiah, so you don't get yourself confused, put parentheses around it. If you have a poly like this, SO4, and it comes out on both sides as SO4, then I need you to put parentheses around it so that you can remember that it's all one. They're all together. So what numbers outside of the parentheses that you don't see? A 1. Careful, okay? Careful. How many bariums? How many bariums? How many bariums? Barium, 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 barium. 1. Okay. How many nitrates? 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 How many? 2. Be careful. Very good. 2. Good. Okay, let's go to the other side. How many ammoniums? I got to put my pretend parentheses to remind myself that these guys are together. How many? What are my numbers that I don't see? 1. All of them. All of them have imaginary 1s around them. Okay? Everybody see that? This is a 1, 1, 1, 1. Why? Because there's no subscripts outside of those parentheses. Good. Where am I going to start balancing? Where? Ammonium, sulfate, barium, or nitrate? Where am I going to start the balancing process? Ammonium, sulfate, barium, or nitrate? Which one am I going to balance? The first one. Very good. What am I going to do to balance? What am I going to do to balance, Oscar? Diamond, Alexia. Very good. 1 times 2. Very good. So that means I'm going to multiply by 2. Very good. So then that 2 is going to go here. And now I can see that these guys are balanced. Who else got affected when I put that 2 for this compound? Who else also got multiplied by 2? The last one. Nitrate. Okay, he got multiplied by 2. And that gives me a 2, right? Now my nitrate's balanced. Now my barium's balanced. Now my sulfate balanced. Very good. And you could see them here, guys. 1, 1, 1, 1. 1, 1. We got a 2 in front of ammonium nitrate, which is what we did, and then a 1. What do you think? What do you think, guys? Try it. If you have silver nitrate reacting with sodium chloride, what is gonna be your products? What are your products? Can somebody try it out on Pear Deck? Can somebody try it out on Pear Deck? And of course, I'm gonna be here to help. Very good, guys. Very good. Somebody's trying it. Ow. I'm getting tired of sitting down. Silver nitrate, AgNO3. Very good. AgNO3. Don't worry about your N's, guys. Don't worry about the handwriting. I know you're working on a computer and it's hard for you guys to write. Very good. Plus, right? Plus means that you're reacting with okay. With NaCl. I see it. I see it. Don't worry about it. NaCl. And it's going to give you. So we are going to move chlorine and he's going to kick out NO3, right? So Ag and Cl are going to come together. All right? AgCl, let's verify those valence. So don't worry, I can help you with that. Silver, 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 silver is right here. Ag plus 1. Okay, so let me go over here so I can help you with the products. So if I have Ag plus 1, and you don't have to write this, whoever's doing the writing. Okay, I'll write this for you. You just write the final outcome. Okay, if I have silver and chlorine, well, chlorine we already know. We know it because we worked with it earlier. It's a -1. Okay, and then that means sodium is with nitrate. Sodium we looked up earlier. Na plus 1. Nitrate we looked up earlier. -1. So what are going to be your formulas? What's going to be your formula for this one? What's going to be the formula for the one on the left? What's going to be the formula for the one on the right? Very good. Very good. Plus. Very good, Alexia. Very good, Oscar. Na. NO. That's fine. Don't worry about your letters. Very good. Okay. Very good. So your reaction is going to produce silver chloride plus sodium nitrate, right? Okay. So I started with silver nitrate plus sodium chloride, right? That's what we have. Okay. Ag is a 1 and a 1. Hold on. Let me make them different colors so you can see them. Okay. So silver, I got a 1 and a 1. Nitrate, if I put parentheses around it, it's got a 1, right? Everybody see that? Sodium 1, chlorine 1. Is this balanced? Is it balanced? It is, right? We don't have to change anybody. We're done. Very good, guys. Any questions on this reaction? Does anybody have a question? Who did this? I want to know who did it. Diamond? Was that you? Thanks, Diamond. All right. So we got, I believe, we have a video. All right. And I skipped to the about 2 minutes in because he just goes over this general reaction, which technically we've already talked about. So I already forwarded a little bit.
Positive ions for each compound switch this. It's the easiest thing to remember. Does it? Is it always positive? I have no idea. But there's no way to prove it up. So we always assume it's always positive. Here's a great example. Lead nitrate plus sodium chloride plus lead chloride plus sodium nitrate. Okay. So what replaced? Lead switch with sodium. Sodium switch with lead. Form lead chloride and sodium nitrate. Now, second place that people always get into trouble with this and with these types of reactions is remembering to balance the charge. Okay? Charges don't necessarily carry from left to right. Notice the chlorine does not have a 2, it has a 1. But here it does. That's because lead is plus 2. Chlorine is minus 1. Cross those charges, it becomes NaCl2. Okay? The nitrate has a 2. Here, it has a 1. Why? So it's plus 1. Two is minus 1. They're equal. They cancel out. Okay? Don't forget that. We'll go over this extensively. And right reaction is hands down the most important thing we do all year.
Yep.
Here's another example. Silver nitrate plus calcium hydroxide equals calcium nitrate plus silver hydroxide. Again, same scenario where crossing the charges is extremely important. What do you see? Compound plus compound plus compound. All of that and another compound. So what you see in the chemical reaction involves nothing but compounds all the way through. It's candidacy, you know this double replacement reaction. Every one of them has their own unique thing. This experiment is an example of a double replacement reaction. In this experiment, you'll see my test tube, I have a clear liquid, which is lead nitrate. On the side, lead nitrate is the only compound lead that's soluble in water, which is why lead is so dangerous to the environment. What I'm going to do is I'm going to add some sodium chloride to it. Sodium chloride, as we know, is also known as table salt. Very simple, little white compound. I dump this little white crystal compound into this, you will see immediately a reaction. And my little white compound has now become, my clear liquid has now become this milky, grainy, kind of powder stuff, kind of looks like a snow globe. You see that it starts to settle itself down. Now what I've created in this experiment is I have created sodium nitrate, which is completely solid. And I created sodium nitrate, which is completely soluble. That's a clear liquid that's forming the experiment. And then is all lead chloride. Now I did not put that much sodium chloride in, but you can see a considerable amount of lead chloride has been created. So it's quite a dangerous problem. This is the second example of a double replacement reaction.
Okay, and I'm going to stop there because we're running out of time. I'm sorry. Okay, so where's the paradigm? Okay, in summary, the double replacement reactions generally take the general form of AB plus CD yields AD plus CB, where A and C are positively charged cations and B and D are negatively charged anions. Your products of double replacement reactions are typically a precipitate, a gas, or a molecular compound. In a double replacement reaction, what type of compounds are usually the reactants? That's question 1. I think there was a typo. And number 2, a double replacement reaction occurs between sodium sulfide and hydrogen chloride. Write the rest of the chemical equation and balance. And here it is, right? Number 3, in a double replacement reaction, One of three possible types of products usually form. What are those three types?